Hi everyone, my name is Thunyaras and I am the R&D manager at PSE for Speed company. Today I'm very excited to share with you a video demonstration of one of our tools, Hybrid-AI-sep, specifically focusing on the problem solution mode. I hope this video gives you a clear understanding of how Hybrid-AI-sep can support your work and accelerate decision making. Thank you very much for your attention, and now let's take a look at the demonstration. So let me put this out. Okay.
For this demonstration, I'll use the example of separating a mixture of acetone and chloroform. I will walk you through the steps of the workflow, so you can see how the tool works in practice. Hybrid-AI-sep offers a number of options that are listed on the left-hand side of the screen. For example, problem solution, educational, process design, etc. I will select the problem solution mode. The first thing we do is click on Start Chat. This begins the problem-solving option offered by the software. After we start the chat, the tool will start to guide us through the workflow steps. Now we are in the chat, problem solution mode. Here, Hybrid-AI-sep introduces itself and the available functions. Note that the text highlighted in blue indicates that explanations are provided for the corresponding text. To proceed, we will need to click on the blue arrow related to the next step. Note also the terms load and save at the top right-hand corner. They are used to open previously saved chat sessions or to save a new chat session. To continue, I'll click on Separation Mechanism. This is where we will tell the tool what kind of problem we want to solve. After we click on Separation Mechanism, there are 3 selection choices. If you're not sure which one to pick, you can click on the blue text, and it will take you to the definition of that term. Feasibility: this type of problem evaluates if the objectives or goals can be achieved. For instance, it checks whether separation of a specified mixture of compounds is feasible, based on the available separation mechanisms. Verification: this type of problem verifies if a proposed separation can be achieved through the in-house model and database analysis. Process design: this option guides the user through the steps to design and simulate the operation of a selected separation technique. In this demonstration, I will click on Feasibility, since we want to check the feasibility of separating a mixture of acetone and chloroform. Note that if in the text box on the right-hand side with blue boundary shows the text view files, then it indicates that Hybrid-AI-sep has additional information in its knowledge base in the form of short descriptions of the involved theory. Next, Hybrid-AI-sep needs more details of the problem we would like to solve. So, we will provide mixture details. Here, we have 4 options. 1. Separate a mixture of 2 compounds, if you already know the mixture. 2. Remove one compound from a mixture. If we only know one compound, the tool will guide us to select the other compound. Note that this option is still under development. 3. Find a binary azeotrope. If you don't know the mixture, the tool will guide you to select a mixture. 4. Find a close boiling mixture. If you don't know the mixture, the tool will guide you to select this type of mixtures. In this demo, we already know the mixture, so we will click on option 1, separate a mixture of 2 compounds. The next step is to specify the compounds in the mixture. We'll do this by using the PSE for Speed database, which is available within this tool. So here, I'll click Search Compound from Database. A search window pops up. To find acetone, I'll search by IUPAC name. I type acetone and select it from the list. Now acetone is selected. I'll repeat the same step to search and select chloroform. Now we can see that both acetone and chloroform have been added as our mixture. Now, let's check the state of this mixture under standard conditions. The tool shows us that under standard conditions, the mixture is liquid. That's because the melting points are below 273 Kelvin, and the boiling points are above 303 Kelvin. This means we can separate this mixture using separation techniques that involve VLE, LLE, or SLE. Selection of an appropriate separation technique can be easier if we know in advance the type of mixture we need to separate. So, we will check if the mixture is close boiling or forms an azeotrope, because they will indicate a difficult separation or not suitable for conventional separation processes like distillation. All I need to do is click on option 1 here. The tool shows that our mixture is close boiling. For close boiling mixtures, the tool suggests possible methods like extractive distillation, liquid extraction, or crystallization. Now let's also check if the mixture forms an azeotrope. The tool confirms that acetone and chloroform form an azeotrope. As the tool found multiple datasets, I will select the azeotrope data at 101.32 kilopascals, which is standard atmospheric pressure. Then, I submit this data. Once the azeotrope is identified, Hybrid-AI-sep suggests that we can use a solvent-based extraction process as the separation technique. As there are different solvent-based extraction techniques, I now need to choose which separation method to apply. The tool suggests VLE-based separation, so that's the option I'll go with. Next, I decide between two VLE methods, solvent-based extractive distillation, or pressure swing distillation. For this demo, I'll choose solvent-based extractive distillation. Note that for pressure swing distillation, I will also need to check if the azeotropic composition moves with pressure, which Hybrid-AI-sep can also find for us. To continue with solvent-based extractive distillation, we need a suitable solvent. So, I'll search for solvents in the database. Two solvents are found in the database. In this case, I'll select 1-hexanol. Now, with the solvent selected, we can check the ternary VLE diagram for a mixture of acetone, chloroform, and the solvent, 1-hexanol. The ternary diagram will show us the distillation boundaries, residue curves, existence of azeotropes, and many more. Hybrid-AI-sep has an in-house tool to competent the ternary diagrams. Theory related to ternary VLE diagrams are also available as an educational aid. To do this, I'll click on Run Process Design Studio to generate the ternary diagram. Here we see the ternary VLE diagram for acetone, chloroform, 1-hexanol. Let me explain how to read this diagram. Each vertex of the triangle represents a pure compound. Any point inside represents the composition of the residue liquid in equilibrium with a vapor phase. The curves in black indicate the residue curves started at different compositions. Note that all the residue curves ultimately end at the higher temperature and start at the lowest temperature. If there are any binary azeotropes, they will be shown on the binary lines of the ternary diagram, that is, acetone chloroform, acetone solvent, and chloroform solvent. It can be noted that the binary azeotrope between acetone and chloroform has been identified. The red curve indicates a distillation boundary, that is, a residue curve connecting the azeotrope with the highest temperature vertex. This means that a feed mixture below the boundary cannot give a pure chloroform product in a single distillation column and vice versa for a feed above the boundary for acetone. As no phase slit is shown in the ternary VLE diagram, this means an extractive distillation column giving acetone as the top product and THR solvent plus chloroform as the bottom product is feasible. Note that a second separation technique is needed for separation of chloroform from the solvent. To check the feasibility of the second separation step, the VLE for the binary pairs of acetone solvent and chloroform solvent needs to be analyzed. Note that Hybrid-AI-sep provides the theoretical background for ternary VLE discograms and binary VLE diagrams and their role on distillation-based separation feasibility. Now we're going to check the VLE of acetone with the solvent, 1-hexanol. To do this, I'll click on Calculate VLE for Hybrid-AI-sep to start the computations. This is the VLE diagram of acetone with the solvent. The x-axis shows the liquid phase composition, and the y-axis shows the temperature. For the VLE diagram on the left. For the VLE diagram on the right, the vapor composition in equilibrium with the liquid composition are plotted on the y-axis and x-axis, respectively. The blue curve is the bubble point curve, and the yellow curve is the dew point curve, the VLE diagram on the left. From these VLE plots, we can see that acetone solvent do not form an azeotrope, and they are symmetric, indicating acetone would be easy to separate from the solvent. The knowledge base has available theory to explain this. Next, we are going to check the VLE of chloroform with 1-hexanol. This is the VLE diagram of chloroform with the solvent. The x-axis shows the liquid phase composition, and the y-axis shows the temperature. For the VLE diagram on the right, the vapor composition in equilibrium with the liquid composition is plotted on the y-axis and x-axis, respectively. The blue curve is the bubble point curve, and the yellow curve is the dew point curve. From these VLE plots, we can see that chloroform solvent does not form an azeotrope. However, the VLE diagrams are not symmetric, indicating that although pure chloroform can be obtained as a top product from the second distillation column, the recovery of chloroform will not be 100% because the blue and yellow curves meet at the high purity end of the solvent. Now that we've checked the VLE of both acetone and chloroform with the solvent, the next step is to confirm which separation technique we'll use. Since the azeotrope makes conventional distillation infeasible, and the solvent clearly points to the needed selectivity, solvent likes chloroform more than acetone, and so it will extract chloroform from the extraction column, and the solvent will be separated from the chloroform in the solvent recovery column. I'll select solvent-based extractive distillation for this separation problem. With the feasibility of the separation technique confirmed, we will select the process design option for design and verification of the selected separation technique. We start with step 0 for the design mode. Hybrid-AI-sep shows the known information, the mixture of acetone and chloroform, and we also selected 1-hexanol as the solvent. Because solvent-based extractive distillation was selected, Hybrid-AI-sep will use the ternary diagram to design the extractive distillation column, using the ternary VLE diagram. Hybrid-AI-sep has knowledge to identify a dashed circle in red on the right side of the ternary diagram. This area on the binary chloroform solvent line indicates the feasible bottom product composition from an extractive distillation corresponding to a pure acetone product as the top distillate product. The higher this point is towards the chloroform vertex, the lower the amount of solvent needed for the extraction. The point of intersection of the line joining the azeotrope point and the solvent vertex with the line joining the acetone vertex with the selected bottom product composition gives the approximate feed composition. The number of stages and feed location is determined using the driving force-based reverse design for distillation columns. The design details are shown for the extractive distillation column. Based on the azeotrope data, the ternary diagram, and the binary VLE calculations, Hybrid-AI-sep recommends how the column should be configured. In this case, the tool suggests a column design with 20 stages in total. The feed tray location is set at stage 10. For the thermodynamic model, it recommends using UNIFAC and the column is designed to operate at 1 bar pressure. These specifications provide the necessary details for rigorous simulation of the extractive distillation column through a process simulator. In step 3, a simulation is performed to verify the extractive distillation column design. It's possible to obtain the corresponding simulation file directly from PSE for speed, or you can use any process simulator of your choice. The simulation results verify the desired purity of the acetone product composition, that there is negligible solvent loss, the energy required, and many more. In step 4, we move on to designing the solvent recovery column. The feed stream entering this column comes directly from the extraction column. Here, we look at the VLE diagram for the binary chloroform solvent system. The diagram shows that achieving a very high recovery of chloroform at the top may be difficult and likely to require high reboiler duty, because the vapor and liquid lines are very close to each other at the solvent-rich end of the diagram. This means that while we do aim for high recovery of chloroform at the top and high recovery of solvent at the bottom, there may still be some chloroform left together with the solvent. Hybrid-AI-sep now designs the solvent recovery column, and then we perform the simulation. The results are shown here. One important thing to note is that at this stage, the solvent is not yet recycled. We are simply looking at how the column behaves with the solvent. This gives us a baseline for evaluating the separation performance before we introduce solvent recycling into the design. In step 6, we will add the recycle stream and a purge stream to complete the process configuration. With these in place, we simulate the entire process flow sheet. In step 7, we see the converged simulation results. Note that these simulation results are loaded from a previously saved file for this example. In step 8, we bring everything together. The ternary VLE diagram, the process configuration, and the string data are shown here. This confirms that the design objectives we stated at the beginning have been successfully achieved. From the ternary VLE diagram, we can also see the feasibility of the desired separation. We need a solvent that does not cause a liquid phase split, has good affinity for chloroform and also high selectivity for chloroform. The solvent does not form an azeotrope with either acetone or chloroform. The only negative side is that in the solvent recovery column, some chloroform will exit with the solvent. Is illustrated between the batch and continuous processes. The green circle represents the total feed to the extraction column. The blue circle indicates the top product stream from the extraction column, while the red circle shows the bottom product. Together with the simulation data, these results ensure that the separation can indeed be achieved. The next step is still under development, but you will be able to perform cost analysis, sustainability analysis, and safety analysis by directly linking Hybrid-AI-sep with ProCAFD. These features will allow us to improve the process design beyond technical feasibility and make it more practical, reliable, and sustainable. Also, the problem solution is rapid, consistent, and correct. Note that at every step, educational notes are available for those who need some theoretical background. Finally, this Hybrid-AI-sep is for problem solution as well as learning and training. It is designed to serve as a complement of the knowledge available in books or what is available from course lectures.
Okay, so I just want to summarize and show you some of the features that I haven't shown you in the video. So I will begin with the start chat. Then I will open the save file by click load here on the right hand side. So here is my save file. And now the save file is open. So here, as we click the mechanism of separation techniques, you can see that on the right hand side, there is the theory node here. So if I click on it, it will lead us to this page. And if we scroll down, you can see that there are two files on theory node. One is for a PDF file and another one is for the video. So I'm going to show you the video of our theory node.
The principal separation mechanism is based on differences in properties of coexisting phases. As the figure shows, there are generally 5 types of separation processes, namely, Type 1, conventional techniques, for example, distillation. Type 2, agent-based techniques, for example, extractive distillation, absorption. Type 3, separation achieved through barriers, for example, filtration.
Okay, so back to the problem solution mode. I'll go through it quickly. So we click feasibility, and then we click on the separation of mixture of 2 compounds. In step 4, we select 2 compounds from the database. And then the azeotrope database found that there was an azeotrope here. And then we also found out about the close boiling and found out about the mixture. We know about the solvent here, and then we remove chloroform and acetone is left out. So before we begin to the design part, we have to select whether we are going to use solvent-based extractive distillation or pressure swing distillation. So we also have the theory node on the right-hand side here about the theory of the extractive distillation. So it will lead you to the same page. So this one, I'm going to show you the PDF file. So here is the theory note about the solvent-based extractive distillation. We also have the notes to explain here on the left-hand side. Okay, back to the problem solution mode. So we also have the theory about the pressure swing here as well, and also the theory for finding the solvent through CMD. And next, the step 0 here is for the design part. So this one is the confirmation. And here we have the ternary diagram with the theory node as well. We've just added this one. And we also have the simulation confirmation of each column here. and scroll down, we have the results of the simulation here. Okay, this is the end of my demonstration, and I will pass on to Roach.